Hello, everyone. Here we are. Anybody there? Flat out. I'm honored to have you in my hangouts. I hope you're still there. And Heath Kamari, thank you. Uh, I really wish to attend all your hangouts, but you come in a bizarre time for my time zone. So uh, here's the question, and let me share the screen. Just a quick question, and then we'll proceed with whatever comes up. Uh, the curvature calculator as a proof. Um, I mean, the question is, if every observation you go out to make matches exactly the curvature calculator, uh, would you have been a flat earther? If there's no such thing as images behind the horizon, every observation you make is consistent with the curvature calculator according to the Earth radius. Would you have said, yes, the Earth gotta be a sphere, or would you have still thought that it's flat and then come with an excuse like the ones ranty flat Earth makes, that there's a compression layer that compresses the targets? I just want to know uh, if observation matches the mathematical proof, because that is a mathematical proof of the shape of the Earth. I just want to know, uh, mathematical proofs are approved uh, by flat earthers, or the majority at least, or not. So that was the question, and I'm open for anyone who pops in. I'll just leave this hangout live for a while. I'm home alone, not doing anything, so you're all welcome. Since we're here, I'd like to show something that Red's Rhetoric showed a few weeks ago. I kinda didn't notice or appreciate how amazing it is, uh, but I've seen it today, and it's really amazing. Let me just put this chat to the side. Anti-crepuscular rays. Of course, this is not the sun, this is the moon. And this is the western horizon. Crepuscular rays. Here's another photo. Also the moon. You can crepuscular ray, and now I want to show something else. a great man. It's called Richard Richard Feynman. Uh, I gotta close slowing down. I don't know how many people know that scientist, but should I be ashamed to say that I only knew of him a couple of weeks ago? Uh, yeah, I'm so sorry for myself that that I'm 45 years old and only now I know Richard Feynman. Of course, there's something wrong with our education system if I don't know him until now, even in a country 10,000 miles from the USA. So I like his arguments and the way he explains things. And one of his videos here, let me get it from here. Now, so
I was now working on something new.
I want you to listen to something. Uh, Here it is.
All the kids were all walking in little parks. I just find it, but my father had already taught me about the names of birds. He once we walked and he says that's a brown-throated thrush. And she's
So he's talking about the names of things, how his father used to teach him a lot of things. And one of them, this story in particular, he's telling him about a bird. So let's hear the story.
She says, know what the name of that bird? It's a brown-throated thrush. In German, it's called a Flügelvögel. In Chinese, it's called a qingmongtong. In Japanese, a tahatahara, and so on. And when you know all the names in every language of that bird, you know nothing, but absolutely nothing about the bird. Then we would go on and talk about the pecking and the feathers. So I had learned already that names don't constitute knowledge. It's knowing the name of something. That's caused me a certain trouble since, because I refuse to learn the name of anything. So when someone comes in and says, you got any explanation for the Fitch-Coulomb experiment? I says, what's that? He says, you know, that the long-lived K-meson disintegrates into two pies. Oh, yes, now I know. But I never know the names of things. What he forgot to tell me was that knowing the names of things is useful if you want to talk to somebody else. So you tell him.
So that's what I wanted to show this. I've just seen it today because I've seen a lot of this going on. Uh, some people go read some definitions and show up to you asking things that I would think I don't know anything about. But later, when I understand what he's talking about, I realize that I know everything about this thing. So the other day, Southern Israelite was saying that the equatorial mount and working on Earth, and Earth is, if Earth is a sphere, then it follows non-Euclidean uh, geometry, and that crushes everything. What blah blah. I don't know what the hell is non-Euclidean geometry. I really had to look up that term after seeing that video, and I couldn't really understand what is that. But the point is, I work on a sphere. I solve geometrical problems of the sphere. I made a SunCalc application and I solved the NLM, which is all dealing with the spheres and ellipses, using the very simple math of sine, cosine, trigonometry that I had in school 30 years ago. So that's what I wanted to talk about. I wonder if anyone here. Okay, so soon I'll wrap it up. Uh, but before I go, when it's time to go, I'll ask another question for flat earthers. If the mathematical proof, that is the curvature calculator, was fine for you and it convinced you that the Earth is a sphere, then why the mathematical proof of predicting sun angles and location in the sky is not enough for you to believe that the Earth is a sphere? Uh, Now, someone may jump and say, okay, now we have two contradicting mathematical proofs. Uh, well, I wouldn't say they are uh, contradicting, because sometimes when the conditions are good and clear, the curvature calculator works perfectly. So, and why is that? Why does it always have to be according to conditions? Whether it shows curvature or doesn't show curvature, because you're looking at a very slight shallow angle, especially when you go 2 inches from the water, like Randy Flat Earth did a couple of weeks ago. So you go all through all these weather conditions at an angle of less than 1 degree. It cannot exceed 1 degree between the horizon and the target. But when you're dealing with the sun calculator, you're dealing with angles uh, like minimum of 67, and all the angles are more than 67 degrees above the horizon. Especially if you deal with the analemma, because that's the limits of the analemma, pointing -23 and +23, and a few degrees to the west and south. Um, if you try to do this with a sun calculator, you'll have a problem when you go for the sunrise and sunset, because again you're looking at the horizon and you have to deal with all these refraction factors. Uh, there is what is called not standard refraction. It's called I think celestial refraction, which is around a half degree. Um, you add this half degree to half the diameter or the radius of the sun, you get a 0.83 degrees. Uh, Let me show you here. Uh, this 0.83 degrees fixes the sunrise and sunset, or not fixes because it's not broken, it just gives the accurate or as close as accurate, because even this 0.5 degree of refraction, it's not like a very strict rule. It changes. It can be up to 4 degrees in the cold areas. Let me find my SunCalc application, and here is the latest version. coming. I hope so. Yeah, just too slow. Didn't I open it? Yeah, okay. Okay, I'm sharing my screen now. All right, here it is. So this is my latest version of my Sun Calc. The inputs in green and the outputs in yellow. And as you see here, I put the geometrical correction, and I call it geometrical correction because it's not only refraction, it's refraction plus the sun's radius. That's 0.57 plus 0.26. So if you have to remove the refraction that in order to work out the sunset and sunrise, you'll have to remove 0.57. Don't remove the whole thing. So this example here is latitude 44, and the sunrise angle is 73. Uh, if we change this, we made it 2 degrees. Now you notice that slight change in the azimuth of the sunrise. Okay, now so the change was 1 degree. Okay, we'll go far north. Let's go. No, before going north, let's go winter. So let's say 1212. So we have the sunrise azimuth at 122 degrees. Let's change the fraction and the whole geometrical correction. Let's change it into 2 and see the difference. So it changed also 1 degree. Let's go far north, 60 latitude. See, the azimuth is 138. Now let's, oh my god, sorry. I have to put the refraction back again first. Yeah. So let's go to 60 latitude. We have a 140 of sunrise azimuth. Let's put this 2 degrees. Now we have 138. You see now it's 2 degrees, not 1 degree as previous. Okay, let's get back. We have the let's call it the standard geometrical correction. I don't like the term standard refraction because what I found that standard refraction is something different to the celestial refraction. I'm not exactly positive on that, but let's be safe. So let's say 66, 68. Oh, this is 24 hours night, so it's 67. So 67, we have the azimuth of the sunrise 178. If we put here 2 degrees, let's see how much it will change. 178 into 171. So that's 7 degrees change in azimuth. And if you're on the equator, there will be no change. The change will only be in time. So let's go to the equator, 0.00001. I cannot put a zero because it will mess up my calculations. Uh, Damn. Let's put it back to 83 first. Yeah. Now, 0.000. Damn. 0.0001 latitude. And let's make it the equinox. So 23.9. So we have here the daylight is 12 hours 6 minute point 6. The sunset is 90 degrees. Now let's put the geometrical correction to 0. Now you see it's 12 hours or 11 hours and 60 minutes. So that's 12, and the direction is still the same. Yeah, heat shield. I'm not sure if you're still there. Yeah, flat out was here. Can you imagine? I think if I wanted more viewers, I would say flat out is coming to this hangout. So this is the first sheet of my SunCalc application, and so anyway, if you don't like the geometrical correction, if you think this is just the fakery or the thing that makes everything works according to the globe, then you don't have to look at this section of the information. Just leave them out. Forget about this and check these information: the solar noon, the sun elevation on zenith, and the sun angles on a specific time. So the solar noon here is 11:52. So after 2 hours, we put here 2, and notice what will happen here when I press enter. So after 2 hours, 2 hours after solar noon, on that day, on the equator, on longitude 30, these are the sun angles. So no, not these. I'm sorry. It's these. Oh, which one? This is, well, let's put it just one. Yeah. So now this is the northern hemisphere, and this would be, I don't know what time is that. Would be the closer to the summer, or let's put it around around the 3 months before or after summer. So let's say uh, 15 August. Let's put this back to 0 again. So on 15 August, uh, on that location, solar noon will be at 12:04.4, and the sun elevation would be 77. And 2 hours after that time, or 3 hours maybe, this is around the summertime, so we look at this section, not at this section. These are the angles. And I'm sorry the interface is kind of hard to work around, but this is because my limitations in the spreadsheet. I'm not that clever. Uh, Here's the equations sheet. Just so messy, I cannot fix it. So I'll leave it like that. And here is the analemma sheet. And as I said before, once the the shape of the analemma is not solely because of the Earth orbit. It's because of the Earth tilt. And I would like to say mainly because of the Earth tilt. Because when you describe it, you say it's a figure of 8. And as I demonstrated before, if we remove this column is the change of the sun direction west-east due to the Earth orbit. So if we made that change into 0, we get a nice figure of 8 that is equal up and down. So that's it for today. I think I'll call it. Bye bye.